The following program is part of Cable in the Classroom, a free service of the cable communications industry and your local cable company.
It's not easy being a reporter for ESPN2 Sportsfigures. Not like those Sports Center guys. They got it so cushy, you know, sitting in their warm little studio, wearing the old suit and tie. I mean, a rough day for these guys is like when the cappuccino machine goes out, you know what I'm saying? I mean, tell me, have you ever seen Dan Patrick dressed like this? I don't think so. Those guys are always talking about the pressure of doing live television. You want to talk about pressure, huh? Try doing an interview at 60 feet underwater.
Sportsfigures.
This thing here on my back and these hoses and stuff, they're scuba equipment. And with them, I can breathe underwater.
Like a fish, right?
Scuba equipment was invented in the 1940s by this guy.
Eventually, knew there wasn't even a word for it. He invented the word too. Scuba. The word scuba means continuous underwater breathing apparatus. Scuba.
The key to Cazot's invention was this. It's called a regulator, and it controls the pressure of the air you're breathing.
And it really worked.
Scuba diving is all about pressure. This tank has a lot of air in it. It's under pressure. In fact, there's 80 cubic feet of air in here. That's this much air all squeezed into the little bit of space inside the tank. Because we squeezed it so much, it's pushing back out against the wall of the tank. And it's pushing with a force of 3,000 pounds for every square inch of tank wall. Look at this. On just this one little square inch of tank wall, there's 3,000 pounds of force pushing out from the inside. That's a lot of pressure.
Scuba diving is all about pressure. It's because of pressure that we need pressurized air, and it's because of pressure that scuba divers need math.
So why would you need math to breathe underwater? Because of pressure.
When we talk about pressure, we talk about force over an area. Hey, Bernadette, how much do you weigh?
110 pounds.
Okay. So Bernadette weighs 110 pounds, and these footprints show the area she was applying pressure to. So how do we figure out the area?
Well, each footprint is 2 inches by 6 inches, making 24 square inches.
Okay, so we could say that Bernadette was exerting a force of 110 pounds per 24 square inches. Or if we divided 110 by 24, that would give us 4.58 pounds of pressure per square inch. So we know that pressure equals force divided by area. You know, Bernadette, I think you weighed maybe a touch more than 4.58. This gentleman behind me here is Dr. Richard Murphy. He's a marine biologist and director of the Jean-Michel Cousteau Institute. He makes his living underwater, so I'd say he knows a thing or two about pressure. Okay, Murph, so right now you are under pressure.
That's right, 14.7 pounds per square inch, PSI.
PSI, okay, so where's all this pressure coming from?
Well, it's the weight of the air in the atmosphere weighing down on us. That's called 1 atmosphere of pressure.
Okay, so do you mean atmosphere like the Earth's atmosphere, or?
Well, we have to make a distinction. It's really a measurement of the weight of the air from the outer limit of the atmosphere down on us right here.
Okay, I have it. I think I got it. So what you're saying essentially is that at every second, on every day, we have 14.7 pounds of pressure per square inch pressing down on us.
Right here, right now, at sea level, it's 14.7 PSI, 1 atmosphere.
He knows what he's talking about. Now, up here in the mountains, there's less than 1 atmosphere of pressure pressing down on you because the air is thinner up here. But the air down here at sea level is denser, so the pressure is 1 atmosphere, 14.7 pounds per square inch. We call the pressure around us ambient pressure. Jessica's hand is 4 inches by 2 inches. That's 8 square inches of area. Right now, this little kid is holding up 8 times 14.7 pounds of pressure. Oh, 117.6 pounds of pressure. Wow, she is really strong, right? Well, actually not really. You see, the pressure of gases and liquids pushes in all directions at once. So there's another 117.6 pounds of pressure pushing up from the bottom of her hand. It equals out. So, Jessica, what does it feel like?
Nothing.
Right. Bernadette standing on my chest exerts just 4.58 pounds of pressure per square inch. Oh, and you can really feel it because there's no pressure to balance it out.
When I stand in the water, my body makes a hole in the water, right? A gas, like air, or a liquid, like water, wants to push into the space where my body is. Like when I get out of the water. See? The water pushes back into the space where I was. Now, air does the same thing, you just can't see it. So when we're in the water, we have the weight of all this water pressing on us. And because water is heavier than air, it increases the ambient pressure.
The area inside this hose is equivalent to 1 square inch. Now, it turns out that a column of salty seawater, 1 inch by 33 feet, weighs 14.7 pounds. Freshwater weighs a little bit less, but since we do most of our diving in the ocean, we'll stick with saltwater. Okay, now, on this 1 square inch of my thumb, there is now an additional 14.7 pounds of pressure, and you can really feel it. What that means is that for every 33 feet you go underwater, your body is under an additional 14.7 pounds per square inch, 1 atmosphere. Now, the air is pressing down on the water inside the hose with 14.7 psi, and the water is pressing down with another 14.7 psi. So this 1 square inch of my thumb is now under 2 full atmospheres of pressure, 29.4 psi.
What that means is that for every 33 feet I go underwater, the pressure in my body is increased by 1 atmosphere. 14.7 pounds more pressure per square inch.
There's an equation we can use to calculate how many atmospheres of pressure you're at any depth in the water. Pressures in atmosphere equals 1 plus the depth you're at divided by 33. 1 is the pressure of the air pushing on the surface of the water. You add that to your depth and you divide by 33, because for every 33 feet you go down, you're adding another atmosphere. Simple, right? Let's try a little experiment. Now, you need air to breathe underwater, right? But if you don't have a tank, you can just use a hose. That's how this snorkel works. But you see, the snorkel only works to the surface. What if you wanted to go deeper? Well, you could just make the hose longer. Let's try it. Oh man, that didn't work. I couldn't breathe at all. How come?
So Murph, what's up? Why couldn't we breathe through that tube?
Well, the problem is the pressure of the water increases about 1/2 pound per square inch for every foot we descend into the sea. Therefore, a mere few feet below the surface, the pressure is so great that our lungs aren't sufficiently strong to pull the air in and compress it so that we can actually breathe.
So what do scuba divers do to make this work?
Well, the key to that is the regulator, okay? And what this does is take very high pressure in the scuba tank and reduce it to the ambient pressure of the water at whatever depth we are. So if it's very shallow, gives us enough air to breathe, and if we're much deeper, then we can take a breath, and the two are adjusted, so all we have to do is pull in with our lungs a little bit, and the air flows automatically.
So as we go deeper underwater, the air we're breathing is under a greater pressure.
Absolutely, and the key is the regulator delivers us air at the same pressure as the water.
This balloon is filled with air. It's now under 1 atmosphere of pressure from the weight of the air around it, just like we are. So what would happen if we took this balloon deep underwater?
It would be under greater pressure.
What would happen?
It would get smaller because the water pressure would push in on it.
Correct. The balloon would still have the same amount of air, but it would take up less volume, less space, because the air inside gets compressed by the ambient pressure. So what would we have to do to fill the balloon back to this size if we were at, say, I don't know, 50 feet underwater?
You would have to have more air.
At greater pressures, you have to add more air to fill out the same space. You see, this balloon here is just like your lungs. As you go deeper, the regulator delivers air to you at a greater pressure. But because the air is under pressure, you need more of it to fill up your lungs.
Air here at 33 feet under 2 atmospheres of pressure. That's twice the pressure amount on the surface, so the air I'm breathing is at twice the pressure, which means I'm using about twice as much air without reserving.
The reverse happens when you go up high in the mountains. Because there's less pressure up here, you get less air with every breath. And that's why it's hard to breathe up here. Whew. If a diver goes to 66 feet, they're now under 3 atmospheres of pressure, so it takes 3 times as much air to fill their lungs. If they dive to 99 feet, they're breathing 4 times as much air. Murph, what's the deepest dive anybody's ever made?
For a diver breathing air, it's over 500 feet.
Okay, 500 feet. So we can figure out how many atmospheres of pressure they're under. 500 divided by 33 is 15.15, plus 1 is 16.15 atmospheres. Whoa, that's a lot of pressure.
That means that a diver is using air 16 times faster than he would be at the surface.
Whoa. This is a balloon. Now, this is the same balloon at 2 atmospheres of pressure. How come?
Because at 2 atmospheres, the air inside is squeezed to half its size.
Okay, if I'm now down at 33 feet, what if I took air from my tank and filled it back up to full size?
It'd be full, but at 2 atmospheres of pressure.
Okay, now, what if I went back up to the surface?
Because it's under 1 atmosphere of pressure, it'd get bigger, it'd expand.
Okay, but it's already full, right? I mean, if it expanded any further... Not a big deal with the balloon, but remember, a balloon is just like your lungs.
Not good.
Not good is right. That's why divers have to be very careful to continue breathing as they ascend to the surface. That way the regulator can continue to provide them with air at the ambient pressure. If the diver holds their breath as they ascend, so if you just keep breathing normally as you come to the surface, you'll be totally safe. So now we know it takes more air to fill your lungs when you're underwater. Twice as much air at 33 feet, 3 times as much air at 66 feet, and 4 times as much air at 99 feet. But you're still only able to carry as much air as the tank will hold. So what happens? This tank holds 80 cubic feet of air at 3,000 psi. Now, here at the surface, at 1 atmosphere, it'll last the average person about, say, 90 minutes. Of course, here at the surface, you don't really need it. But what about when you dive?
You're going to use up air at a faster rate.
Okay, so how long will the tank last?
It depends on how deep you dive.
Okay, so we could use our equation to figure out how many atmospheres we're at. Then use that number to figure out how long the tank will last.
If you knew the tank would last 90 minutes in 1 atmosphere, then at 33 feet, 2 atmospheres, it will last 45 minutes. It's simple.
It's very simple, okay, but let's say that we were at 50 feet.
Just use your equation, always dividing 90 by what atmosphere you're at.
Correct. Sounds simple to me. We already know our equation to figure out pressure in atmospheres. 1 plus depth in feet divided by 33. And we're going to divide 90 minutes by however many atmospheres we're at to get our time the tank will last. Let's say we're diving at 50 feet and plug that into our equation. 50 divided by 33 is 1.51. Plus 1 is 2.51 atmospheres. Then we just divide 90 by 2.51, the number of atmospheres we're at. And we find that our tank will last approximately 36 minutes at 50 feet.
Well, that's not really how we figure out how long a tank will last, because there are many variables. The age of a person, their size, how cold the water is, how fatigued they are.
Okay, but dive time is important, right?
Oh, absolutely, and it has to do with the body's absorbing nitrogen gas from the air that we're breathing under pressure. And that gas dissolves in our blood, And of course, the longer we're down, the more gas that comes into our blood. And as we ascend to come back to the surface, that gas can come out as bubbles, like when you open a can of soda. And if those bubbles get lodged in our joints or in our brain, we have a major problem. That's called the bends.
Okay, guys, so what did we learn?
That the ambient air pressure at sea level is 14.7 psi.
Very good.
That is called 1 atmosphere.
Okay.
And that for every 33 feet you go underwater, you're under an additional atmosphere of pressure.
And so's the air you breathe, so you gotta watch your downtime.
So if you just understand pressure, you can take a lot of the pressure out of diving.
I got the sense of the Rick and Morty, Steve Lewis, or students, someone that's seen Morty, for helping us out with ESPN2 Sports Figures, Meta Longer Pressure.
We'd like to thank all the sports figures who participated in today's show free of charge. ESPN Sports Figures is presented commercial-free for educators to tape and use in the classroom. Comments or questions about sports figures? Drop us a note at ESPN Plaza, Bristol, Connecticut, or the email address on your screen. To order a free teacher's curriculum, call 860-766-2000, or better yet, go to the Sports Figures website for all sorts of cool stuff. This has been a presentation of ESPN, the worldwide leader in sports. For more, log on to ESPN.com, part of the Go Network. Go.com. Sports Figures. Put your brain in the game.
The preceding program is part of Cable in the Classroom, a free service of the cable communications industry and your local cable company.